Chemical Bonding, featuring Brianna Delgado, Cynthia Garcia, and Cristina Guerrero for Chemistry 1311 with Dr. Delgado. So to start off with our PowerPoint, we are going to go into what is a Lewis dot symbol. A Lewis dot symbol uses dots to represent valence electrons. We all know that elements have many electrons, but the valence electrons are the only electrons that are involved in the chemical reactions. The Lewis dot symbol is what helps us to understand each element's chemical properties. In order to find valence electrons, we must look at each group. As we know, groups are what goes up and down and periods go across. So, looking at group 1, which starts at hydrogen on the far left of our periodic table, we see it is group 1, therefore it has 1 valence electron. Group 2 has 2 valence electrons. We're going to go ahead and skip all of the elements in the middle, the transition metals. Although they do have valence electrons, those are harder to find, and we will not be expected to find those, at least for this chemistry class. Moving on to group 3, those would have 3 valence electrons, and so on, all the way to group 8. Now, all of the elements in group 8 have 8 electrons, with the exception of helium. Helium only has 2 valence electrons, even though it is in group 8. So, just remember, when trying to find valence electrons for the Lewis dot symbol, or for any reason, the valence electrons is the same number as the group that the element is in, with the exception of helium, who only has 2 valence electrons. Moving on to ionic bonds. Ionic bonding involves the electrostatic attraction of 2 oppositely charged ions. It is the complete transfer of valence electrons between the 2 atoms. In an ionic bond, you have an anion and a cation. The nonmetal will always be the anion, and the metal will always be the cation. If you look on the right of the screen, we have an example, which is Na and Cl. A sodium atom and a chloride atom are an example of ionic bonding. To further elaborate on ionic bonds and how to form an ionic bond, we must remember ions do not suddenly appear and then disappear again. They are simply transferred from one atom to another. This can be thought of the same way that opposite poles of a magnet are drawn together. So are the 2 oppositely charged atoms. As we can see in this example, magnesium and oxygen form magnesium oxide. Magnesium transfers its 2 valence electrons to oxygen, and the remaining ions are electrostatically attracted to each other, which then forms the ionic bond. As you can see, the charge of 2 positive and 2 negative balance each other out, ultimately leaving a neutral charge. The same goes for our bottom example. If you look at calcium and chlorine, calcium would give away its 2 valence electrons to the chlorine atoms. As you can see, we would end up with a 2 positive charge and then 1 negative and another negative. So again, this would ultimately balance out to leave an overall neutral charge. Now we're going to go ahead and move on to covalent bonds. Now, these bonds are found only in covalent compounds, and this can be defined when 2 electrons are shared by 2 different atoms. So this is basically the coming together and the sharing of electron pairs to create a covalent bond. Because as we know, all elements are trying to reach 8 valence electrons so they can be stable like the noble gases. So an example of a covalent bond would be chlorine and chlorine. Since they both have 7 valence electrons, they need one more in order to attain stability and to complete their octet. The two chlorine atoms would come together to form a chlorine molecule, sorry about that. Since they share the one pair of electrons, this would form a single bond. Another example of covalent bonding would be oxygen and oxygen. They would be sharing two pairs of electrons, and that would be a double bond. And then so on and so on. A nitrogen molecule, which would be the two nitrogen atoms coming together, and they would share three pairs of electrons, so they would form a triple bond. Next, we are going to move on to polar covalent bonds. So a polar covalent bond is basically just when the electrons are not shared equally between the two atoms. Because we already learned that the electrons are shared, but now we know it's not always going to be equal. So it's basically, when you think of polar covalent bonds, just think of the uneven sharing of the electrons. So sometimes one element is much stronger than the other element, which creates almost like a tug of war between the two electrons in the bond. So this is based off of or because of electronegativity, which is something that we will learn later on in the video. Basically, we can calculate the difference in the electronegativity, and this can help us determine whether or not the electrons are going to be shared evenly in the bond. So as you can see in our pictures on the bottom, when hydrogen and Cl are combined, there is an uneven sharing of the electrons. So Cl has more. And then on our next picture, as you see, there is a nonpolar covalent bond with hydrogen and hydrogen, since they share their electrons evenly. And as you can see on B, that is an example of a polar covalent bond because our F element is stronger than the hydrogen. So again, the electrons are not shared evenly. Now that we have gone over the different types of bonds, we have a question to review. Which has a full charge on the ions? A, polar covalent bonds, B, covalent bonds, or C, ionic bonds? The answer in this case would be C, because we know that in an ionic bond, the ions are transferred completely. We know that in a covalent bond, they are shared, and in a polar covalent bond, they are shared, but not evenly. Alrighty, now that we have gone over that, we're going to go back really quickly to the Lewis dot symbols and the valence electrons. I'm going to go ahead and ask you guys a few questions just to make sure we really understand this concept, because it is the basis of what we're going to be learning further on in the slide. So, if we were given the element sodium, how many valence electrons would sodium have? Correct. Because sodium is in group 1, it would have 1 valence electron. If we were given the element oxygen and asked, how many valence electrons does oxygen have? What would our answer be? The answer would be oxygen has 6 valence electrons because it is in group 6.
So let's move on to electronegativity. Electronegativity is an atom's tendency to attract electrons to itself. The reason why an atom wants to attract electrons is in order to have a stable electron arrangement. Everybody wants to be like a noble gas. Noble gases have 8 valence electrons, so our magic number is 8. In other words, some atoms are more likely than others to pull electrons to itself, so they can imitate the cool kids. Some of the previous trends we have discussed in Chapter 7 relate to electronegativity. The previous trends of ionization energies and electron affinity will help us understand the correlation between them and electronegativity and how to determine the different types of bonds. A particular chemist named Linus Pauling gave us a way to obtain the relative electronegativities of most elements. We say relative because they're estimated numbers. In the next slide, we will see some of the values and how we can make a connection with past trends. Two of the elements we can use as landmarks of relative electronegativity include fluorine and francium. In this following chart, fluorine is the most electronegative element, while francium is the least electronegative element. As you can see in Pauline's chart, the highest values are located with nonmetals in groups 5A to 7A. Why do you think this is? I'll give you a few seconds to think about it. So a brief refresher on two previous trends we've discussed. Remember, electron affinity is an atom's tendency to pick up electrons easily. Also, if you remember, we also learned about ionization energy, which is the atom's tendency to resist losing an electron. Elements with less than 8 valence electrons have high electron affinity and high ionization energy. Simply put, they want electrons and they will resist losing them. So going back to the question, the highest values are located with nonmetals in groups 5A to 7A because they tend to be elements that want to attract electrons in a chemical bond so they can look like a noble gas. Now in groups 1A to 2A, we have mainly metals such as sodium, lithium, and potassium, etc. These elements are less stingy with their electrons, so they're willing to share. Trend-wise, their electron affinity, ionization energy, and electronegativity will be low. We don't have to memorize the upcoming chart, but if you will this chart, but if you will remember, fluorine's value is high and francium's value is low, you can remember the general trend for electronegativity. This trend tends to increase from left to right across a period and decreases from bottom to top in a group. Transition metals tend to not follow the trend, but that's easy to remember since they're weird anyways. So how do these trends help our understanding with bonds? Using Pauline's chart, we can calculate the electronegative difference and thus obtain the type of bond two or more atoms will make. When the difference is less than 0.5, we will have a nonpolar covalent bond. A nonpolar covalent bond tends to happen with atoms of the same element. When the difference between two atoms is equal to 0.5 but less than or equal to 1.9, we have a polar covalent bond. These bonds are typically seen with atoms of similar electronegativities. Lastly, if the difference is 2.0 or greater, we have an ionic bond. An ionic bond is easy to remember since it usually involves a metal and nonmetal. Now let's look at the following atoms, HCl and Kf. Using the values in Pauline's chart, we obtain a difference of 0.9 between hydrogen and chlorine. This value shows that HCl is a polar covalent bond since its difference is more than 0.5 but less than 1.9. And potassium and fluorine, the difference in value is 3.2, which is way more than 2.0, making this an ionic bond. Now let's begin to look over Lewis structures. These structures are used to predict the type and number of bonds two or more atoms will combine to make. Because only an atom's outer regions come into contact when bonding, we will only be looking at valence electrons. Let's look at the image of the two fluorine atoms pictured. How do we obtain valence electrons? First, we look to see where the atom is located on the periodic table. For example, fluorine is in group 7. So the number of valence electrons fluorine would have would be 7. Since we have 2 fluorines pictured, we will have a total of 14 valence electrons. The valence electron value is 7 times 2 fluorine electrons equals 14. So when these 2 fluorines bond, they will have a total of 6 lone pairs and 1 single bond. Basically, electrons located in the middle of 2 atoms are bonds. Any electrons left that are not being shared are known as lone pairs. So with this particular example, we have 1 single bond and a total of 6 lone pairs of electrons. To reiterate, electrons are represented by lines or as pair of dots in a Lewis structure. A line will represent 2 electrons and is usually used to show a bond, while a pair of dots is usually used to indicate a lone pair. In this slide, we will be looking at carbon dioxide and carbonate. The first step here is to obtain the number of valence electrons in each atom. With carbon dioxide, we have 1 carbon and 2 oxygen atoms. Since carbon is in the 4th group, we will have 4 valence electrons. Oxygen is in the 6th group, and we have 6 valence electrons. But because there are 2 oxygens, we will have a total of 12 valence electrons for oxygen. So we add oxygen's 12 valence electrons and carbon's 4 valence electrons, and we'll have a total of 16. Now we can draw the skeletal structure. Because this is a simple compound, we can deduct that carbon will be our central atom with the 2 oxygens bonding with carbon. We need to make sure each atom is happy, and to do that we have to check that each atom has 8 valence electrons. The correct arrangement will have 2 double bonds between carbon and oxygen. We'll have 2 double bonds between carbon and oxygens, and oxygen will have a total of 4 lone pairs. For carbonate, we do the same. We calculate the total valence electron, which is 22, but because of the -2 charge, we will add 2 electrons. So the total will be 24. When drawn out, carbonate will have 2 single bonds, 1 double bond, and 9 lone pairs. Each atom is happy regarding the octet rule. So let's practice more. The more we draw these Lewis structures, the better we'll get. So I'll be transitioning to paper so I can show you how to do the Lewis structure for an ammonium ion. So the ammonium ion, nitrogen is in the 5th group, so 5 valence electrons. Hydrogen is in the 1st group, 1 valence electrons, but there's 4, so we'll be multiplying these 2. We get a total of 9 valence electrons. Because there's a positive charge, we will subtract 1 valence electron for a total of 8. When we draw out the structure, this particular ion, nitrogen, will be in the middle since there's only 1, and it'll be surrounded by the 4 hydrogens. So let's see how many electrons we've used so far. This bond indicates 2 electrons, so 2, 4, 6, 8. We've already used the 8 valence electrons, so we just need to make sure that each atom is happy. We don't have to rearrange it. Nitrogen has 2, 4, 6, 8. It fulfills the octet rule. Hydrogen only needs to have 2 electrons, so each hydrogen does have 2. Next, to figure out what type of bond there is, we will get the electronegativity of nitrogen and hydrogen. Using your tables, nitrogen will give you 3.0 and hydrogen will give you 2.1. The difference is 0.9. This value falls into the polar covalent bond. And then next we'll do our vectors towards least to most electronegativity. Our vector from hydrogen goes towards nitrogen for all four. With values of 0.9.
How to make a Lewis structure. First, find the total number of valence electrons. Then put the least electronegative atom in the center of your structure. Hydrogen always goes on the outside of the structure. Put 2 electrons between the atoms to form a chemical bond. Complete the octet on the outer atoms. If the central atom doesn't have an octet, move electrons from the outer atom to form double or triple bonds. First, find the total number of valence electrons for the molecule you are using. You will need to use the periodic table to figure out how many valence electrons are in each element. Let's use H2O. For example, hydrogen is in group 1 on the periodic table, so it has 1 valence on the electron, but the subscript tells us that we have 2 hydrogen, so we need to multiply that by 2. Oxygen is in group 6 and has 6 valence electrons, and when we add 2 plus 6, we get a total of 8 valence electrons for H2O. Remember, valence electrons are the outer shell electrons. They are the ones that form chemical bonds. Put the least electronegative atom on the center. Remember, fluorine is the most electronegative, followed by oxygen. So as you move away from the fluorine and the oxygen, the atoms become less electronegative. That means those atoms will go at the center. Something important to know is that hydrogen always goes on the outside of the structure. Next, put 2 electrons between the atoms to form a chemical bond and complete the octet on the outer atoms. 1, 2, 3, 4, 5, 6, 7, 8. This giving us a total of 8 electrons. If you have used up all your valence electrons and you still haven't completed the octet for each atom in the molecule, then you move some of the electrons from the outside to the inside and share them to form double and triple bonds. Resonance. This is what we use to describe delocalized electrons of the certain molecules that can't be expressed with one single Lewis structure. Resonance is used when you need more than one Lewis structure to represent a single molecule. Resonance structures are simply alternative Lewis structures for a given ion or molecule. We can draw all resonance by drawing all of the possible Lewis structures. Electrons that can be moved between adjacent atoms, resonance structure are lone pairs. The example we're going to use is ozone. We can draw O3 with a double bond on each side. We can draw O3 in different ways. We can draw it with double bond on the left and single bond on the right. We can draw it with double bond on the right, that it mirrors the image of the last one. The octet rule. The octet rule allows us to predict how atoms will form chemical bonds to make molecules. When atoms have 8 electrons in their highest energy level, they have an octet. Atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons. Noble gases all have a full octet. The octet rule exception. There are three types of molecules that are the exception to the octet rule. Electron deficient molecules, molecules with an odd number of electrons, example nitrogen, molecules with expanded valence shells. Hydrogen and helium are an exception to the octet rule. Hydrogen only needs 2 valence electrons to have a full outer shell. Helium has 2 valence electrons in the outer shell, and that shell is full. Molecules with an odd number of electrons are an example of nitrogen, has 5 valence electrons. Another important exception is the expanded octet. An expanded octet is when an atom has more than 8 electrons surrounding it. These are found in periods 3 and higher elements because they have d orbitals. An example would be sulfuric acid. Bond enthalpy. This measures the stability of a molecule, the enthalpy change required to break a bond in 1 mole of gaseous molecule. Bond enthalpy is the amount of energy required to break 1 mole of stated bond. A bond enthalpy is always positive, which means you will have to add energy to break a bond. When you reverse the enthalpy, it will be a negative because we will take energy. How to find the bond enthalpy? First, determine the broken and formed bonds for our example. We will be using the reaction between hydrogen and bromine. Remember, a single atom does not have a bond. It is the bond between 2 atoms that has energy. First, we need to find the bond energy for H bond, Br bond, and H and Br bond. H bond is 436. Br bond is 193. HBr bond is 366. We are going to multiply by the bond broken. In this case, it will be only 1. Now we will add up all the bond energies. HH, 436, BR, 193, giving us 629. We also need to multiply the bond energy by the number of bonds formed. We have 2 HBr bonds, so we will multiply 366 times 2, giving us 732. And we subtract the formed bonds from the broken bonds, 629 minus 732, which will give us a negative of 103. The final bond energy is negative, making it an exothermic reaction. Question. Write out the Lewis structure for beryllium fluoride, BeF2. Beryllium fluoride. The Lewis structure for beryllium fluoride. On the periodic table, beryllium is in group 2 and has 2 valence electrons. Fluoride has 7, but we have 2 fluoride making a total of 14. If you add 2 plus 7, times 2, it's going to give us 16 valence electrons. Beryllium is the least electronegative, so it will go in the middle, and fluorine will be on the outsides. To start, we will put 2 electrons to form a chemical bond. Now we have used 4, so we can start putting them on the outside. Beryllium does not need 8 electrons to show, but we will still have a total of 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I can also draw the Lewis structure in a different way. I am using the same number of valence electrons, but by sharing I've created double bonds between beryllium and fluoride, and this still gives us 16 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16.